Awesome. We can get started. RSNA 2022 Cervical Spine Fracture Detection. I say those words just to make sure I can hear myself. So let me check if I'm live or not. I can hear myself. Perfect. Everything is on time today, which is good. Let me take off my headphones and get started. Welcome back, everyone. If you're watching live, Merry Christmas if you celebrated. If you're watching the replay, still Merry Christmas to you. We'll go through top solutions. We usually go through top solutions as a study group. The plan for me is to study with you all together and try to understand how best Kagglers or how top rated Kagglers approach different problems. And we try to condense those tricks or secrets from everyone. Pragya says, Merry Christmas. Merry Christmas to you as well. Um, Rabia has taken the seat. Thanks for joining. So what we try to do is we try to learn how top Kagglers approach different problems and things for them. So for today, I chose RSNA 2022, which is the first RSNA competition of this year. There's another one happening right now. Alex says Merry Christmas. Merry Christmas to you as well, Alex, and Merry Christmas to you, Mayank. I haven't seen you in a while, Mayank. It's great to see you in the chat. Mayank and I used to do a lot of study groups together. Good evening to you, Yantran. Thanks for joining. Cool. So the reason for picking this competition is there's a RSNA competition happening right now. It is somewhat similar, not exactly. If it was very similar, everyone would have just taken the baselines from here and started there. But the plan for me is to go through all medical image-based Kaggle competitions. Because if you look at the current RSNA competition, it's you working in medical images, and my understanding is there's always some trick hidden here and there that we can learn from there, or even in general it's good to know what top Kagglers use, because this knowledge can come in handy anywhere. So enough justifying the logic. Let's get started. If you're new or if you're just watching this live stream, I spend the first half setting up the problem statement, explaining the context, and then we start going through the top solutions in the later half. So for now, I'll give the context, explain why this was a challenging problem, what baselines existed, what approaches existed, and how you could have gotten started at that time. So the goal of this competition, as the organizers put it, or if you look here, it's to identify cervical fractures from scans. And the organizers say over 1.5 million spine fractures occur annually in the US, and over 17,000 of spinal cord injuries annually. This is a really serious problem, because spinal cord injuries can be very life threatening, if I may, or they can cause severe effects to the person. So working with these images, having that knowledge or building those models is of real importance. And usually I assume it takes a lot of domain knowledge, a lot of training, as it does for any medical problem. They say imaging diagnosis of an adult spine fracture is now almost exclusively performed with CT instead of X-rays. And quickly detecting and determining the location of vertebral fractures is essential to prevent neurologic deterioration or paralysis after the trauma. So this is very serious and very helpful at multiple levels, as you can see. They talk about how the data set was created, and this time I actually, for the first time, I looked at the acknowledgements. They point out 12 research institutes from 9 countries and 6 continents provided the de-identified CT studies, and they marked that on the globe. So one could argue that based on the statement, hey, this is just these are just studies from one country. No, that's not the case for this competition. As you can see, the data comes around the globe, and it's a wide discussion that I won't go into. But you could always have problems of biases. If you use just a data from a certain demographic, let's say just one country, it could bias your models towards that. But it's good to see that the models are the data is coming from different countries and continents. Mayank says hopefully he'll be a regular. I hope so too. It's great to see you. I always enjoyed learning with Mayank. We used to do Python for data analysis study groups together, and we had some really nice discussions there. Maybe we'll start again next year. Who knows? Consider subscribing. You'll be notified if I start that study group. Um, so here's the description of the dataset. They say the goal is to identify fractures in CT scans of the neck, both at a single vertebrae and the entire patient. The train CSV contains the study instance ID and patient overall. And then you have C1 to 7, which gives you the info if the vertebrae is fractured or not. And then inside the test set, you have the row ID, you have the study instance ID, and you have to you given the prediction type, which tells you which one of the 8 target columns need a prediction in this row. I'll show some EDA kernels and we can start off of that. But as you can see, this is a pretty large data set, and that's very common to DICOM files. So a lot of diagram processing or approaches around that was involved. Sorry. Soros says they wanted to participate, but the data size uh, blew them away. That can be daunting, but that's a if you look at the discussions, let's take a look. Data set. So Osif, who I was just going to talk about in a second, by the way, this awesome guy in this photo. I got to meet him. Unfortunately, we didn't hang out so much because I was flying the next day, but I got to hang out a little bit with Osif in Barcelona at Kaggle days. He's a legend and writes amazing kernels. So shout out to Osif, and I'll just come back to his kernel in a second. But he, as you can see, uploaded a dataset of 18 GB and 55 GB, which ironically is somewhat reasonable. So Kagglers are usually giving datasets that you can work with to some extent. This 18 GB is much more reasonable than 330 GB. So that could have been a starting point for you, but usually look for subsample datasets or datasets of smaller image sizes. So let's do one thing instead of I'll come back to Osof's kernel, but let's use Andada's kernel to know about the dataset. So Andada writes amazing EDA kernels, and I'll use this chance to just explain the concepts or explain the competition using her kernel. So we have to predict fractures from in the vertebrae from C1 to C7, and these are the cervical vertebrae. There are thoracic vertebrae and lumbar vertebrae as well, and then there's the sacrum. So we are only concerned with C1 to C7, and that's where we're trying to detect fractures. And there's some more images about some more terminology. If you go to discussions, the most one of the most popular ones was a quick review of cervical spine anatomy, and Asmine had given a lot of info about all of these things. So about every specific bone C1, C2, C3, C7, and this was quite scary to look at. So I was interested to see if any of the winners used some domain knowledge. Turns out they did not. So as you can see, even as an outsider who doesn't know very much about bioimages or biomedical images, you can probably still do really well without knowing what left uncinate processes or what is the articular surface of right unciate process. I am struggling to pronounce them already, but I hope that tells you. I hope that gets the point across. So coming back to this kernel, and Dada has done some interesting plots that I'll just highlight here, and we can use that to understand the data set. So once more, this gives the training data frame tells us whether or not there is at least one vertebrae that is fractured, and which of the vertebrae, if any, are fractured. There are 2019 unique IDs. Here's the cool bit. So some images also have a training bounding box, and bounding box coordinates are given with the exact location of the fractures. So after this, I'll also remind everyone of a few concepts around object detection and segmentation. We'll see many teams use that. But you had these for some images, and there were 2019 folders containing the DICOM CT scans of the patient. So you would get a folder like so, where you'd have the study instance ID, the if there's a fracture present or not. And then, as you can see in the first one, there are two fractures. In the last one, there's just one fracture, and that's true to the other two examples as well. For the third example, there's no fracture, and if you see zero here, you should see zero everywhere. So one denotes if there's a fracture or not in a particular vertebrae, and in overall, it refers to if there's a fracture at all or not. In this bounding box dataset, you're given 7,000 annotations, and there are no missing values. So you can see the bounding box dataset here. You're given the x and y coordinates and the width and height and the slice number. The slice number is relevant here because in CT scans, you have a 3D scan of the image. So after this, I'll show a kernel where someone had come up with a very cool approach to plot the 3D visualization of the vertebrae. But the slice number is relevant because how CT scans, as I understand, work is you take slices across what you want to scan. So every slice is like a 2D plane, and then you stack them together like a book. So it's like papers stacked together where each slice is given a number, and that denotes how your height along the z axis, if you may. So there's some details about that. Analyses that in data are shared. So class is balanced. There's a 50-50 ratio between patients with and without fractures. Sorry about that. C7, this is the bone with the most frequent injuries. C3 is the bone with the least number of injuries. As you can see, here are some plots about fracture flags. So there's almost a 50-50% split. As you can see, you can round it off to 50-50. Zero, the blue bar denotes that a fracture is not present. And the purple one is the number of fractured examples of fractured vertebrae in the dataset. C3 has the smallest number, as you can see, and C7 has the largest. Some more takeaways: injuries in one bone out of 961 cases, at least one fracture occurs, and very few cases have injuries in four bones or more at the same time. So this is a graph showing the total number of bones fractured. As you can see, the largest is just no fracture at all. After that, it's one bone is fractured, and from there it dwindles on. So it's kind of rare that you have more than three bones fractured, as you can see from this plot. After this, there are some plots along or some explainers along. Let's take a look at the DICOM dataset and understand what's going on there. So this is what it looks like if you plot those out. I was talking about the slices earlier. You have all of these slices that are somewhat stacked together. So that gives you the 3D image. Now this is a bone, but this is just a 2D representation of the bone. So that's how you showcase or you basically can plot these. Sora says Kaggle discussions save a lot of time with amazing insights. Yeah, for sure. Many Kagglers put in a lot of time there. So I hope these live streams give some insights as well. And hopefully that's why you're joining. Another example of the slices. So as you can see, there are a large number of slices on all images. The first one has 32, this one has 55. And inside the metadata, so as you can see, each file is named like so. And inside the numbering, there's a way to tell the slice number as well. Some details about the DICOM metadata. So DICOM files come with some metadata. You could also have age and more things here. Sometimes gender is also shared in the metadata. That totally depends on the organizer, but there's a standardized format where all of these details are shared already. And that's why there are many frameworks, if you will see, of how to work with DICOM images or how to effectively read those in memory. And that's another reason why Soros, these are so large in size, because they carry a lot of metadata in them as well. So the rows tell you the height of the image. There's a width. There's a unique identifier, date when this was scanned, the slice thickness, the instance number. So that gives you the slice number for that particular image. The image position, so the x and y z coordinates of the upper left hand corner. And when you're working with 3D pixels, that is called a voxel. So this tells you the center of the voxel transmitted of the image. There's also image orientation, which tells you the direction cosines of the first row and first column with respect to the patient. I have no idea what the last point means, but this is what it does. That's the definition of that. Also, I would have looked it up, but I didn't find any team using this. So I did also read through some top solution repos, and to the best of my knowledge, no one used this. So it's I leave it at this. This is all that means. Um, there are also some more details about the distribution that are worth looking at. So the distribution for DICOM files on study instances is skewed to the right. 78% have 200 to 400 slices. Only 6% have less than 200, and there are 50 instances with more than 600 slices. So if you plot this, so this shows the example, the number of DICOM files and the number of slices inside of them. So remember the 3D papers. This is slightly skewed to the right, as Rada pointed out. And this is another cool plot to see. So the number of slices and the distribution of the DICOM files. There are only 50 with more than 600 examples, as you can see here. And the between these two, and data claims that 80% of the data exists here, apparently. The image size, 99% of the images have a 512 by 512 size. This is pretty cool to see. Sometimes you have much larger images. So you have like 3000 by something images, and then you have mixed image sizes. So there are like independent discussions of what image size you're working with. Usually, large image size gives a large boost. But here, like 512 by 512, with a disclaimer that would require a lot of compute, is still like a reasonable size to work with given current competitions. So all images were 512 by 512. And here's another plot confirming that. So all of the DICOM files have the same creation date, as you can see here. Now there's a study of the bounding boxes. So 50% of all slices have 25 or less bounding boxes per study, and 16% of slices have less than 10 bounding boxes per study. There are 6 outliers with more than 100 bounding boxes per study. So here's another plot about that. I'll scroll past this and you can take a look if you want. And you can see the bounding boxes like so. So these would tell you where the fracture occurs, and you have all of these represented like so. So as you can see, for all the images, there's like a tight box around where the fracture occurs, and you can many teams have created segmentation approaches to work with this, and you could figure out ways of how to do this in different fashions. The reason why these fluctuate so much, right? Like as I scroll through, you can see the shape of the bounding box is also changing, because remember the fracture is like a 3D crack in the bone, so it exists at one location, and these images are 2D. So that's why the bounding box shape also changes from slice to slice. So it took me a second to like understand that is that like some mistake in labeling or something like that. No, that's not the case. That's just because we're in 3D, the crack occurs. So this should I had some more kernels open, but you're welcome to take a look through this one by Samuel. I'll remember to upload it. And there's one more by Laura who works at H2O as well. And Laura always writes awesome kernels. I really enjoy her work as well. She, from what I know, she's also interested in medical XML problems. So that's you should always check her work out. But I think this is a good enough overview of the competition. Some more things worth pointing out. This was a inference based competition, which meant that you are given 9 hours of submission time. So you can train your models offline and then you upload them to Kaggle and they're supposed to complete inferencing within 9 hours. So from what I know, you had about 1500 examples in the test set on which you had to run the inference. So there was one limiting factor there. And this dictates a lot about how much ensembling you can do, especially when you're working with medical scans, right? So for the current RSNA, there was initially this challenge of if you were trying to resize the images or convert them, it would take 7 hours on CPU just to convert them into a format you can work with. And then people, of course, Kagglers came up with approaches around it. So all of these things combined together build up a lot of constraints on what you can work with. The evaluation was a weighted multi-label log loss, and there's a formula representing that and how they expect the submission file to be. So what I'll do now is we can take a quick refresher on how do you work with semantic segmentation problems and also bounding box datasets. So for that, what I've done is this is like one of my favorite ways of explaining concepts because literally Chishin and Philip have built this tool, and I keep falling back to it, but it's like one of the easiest ways to explain all of these things. So I've picked a standardized dataset for semantic segmentation, and I can look at all my experiments here. This is called hydrogen torch, if you're not aware, by the way. But what I'll do here is I'll create an experiment with a dataset I've already loaded up. So that would be the fashion image one. And if I go to master settings, the goal here is like to show you all what settings can you apply when you're working with semantic segmentation problems. Um, so I'll use the grouped k-fold CV strategy, and you can decide the folder there, the folder that you want to work with, and the number of folds you want to train your model across. I'm just giving a demo, so I'll keep it short. Now, this one comes with RLE masks, but you could have different form of masks provided, and you can work with those. And by that, it's not really bounding boxes here, but it's more of a mask, and people have converted masks for this competition. You could have a bounding box as well, and then it becomes an object detection problem. That's what I referred to. So in that case, I would select an object detection case here and work with that. And as you could see, you could work with a lot of different problem types in hydrogen torch. I'll set the image size to whatever I think is a nice one, 512 by 512. And I leave image normalization to simple, augmentation strategy, soft, sounds good. I can enable mix up here, which is always a good idea. And then I can fiddle with the settings. These are usually good, I found, so I leave it at that. Here's some thing to note. So usually I have different backbones that you can work with. And of course, this tool has the best one. So that's why I wanted to bring this up. So you could have efficient backbones, ResNets, SE ResNext, or DenseNets. We'll just work with ResNet. Some teams used EfficientNet small. Some teams had used, I think, fancier mixes. And Chishin, who actually won the competition, he figured out 3D CNNs are a cool approach to this as well, and he settled on 2.5D CNNs. But then he decided, okay, 3D CNNs are worth exploring, so he shipped that feature to this tool, and that should also be out soon. So we could directly work with 3D CNNs as well if we wanted, because Chishin thinks it's worth having, so of course it's there in the data in the tool. Usually, when you're working with this, you could have the following loss functions. And I point these out because these will come up again when we're going through the top solution. But BCE dice, BCE LOVAS, and dice are the most common ones. And we'll see this in the top solutions as well. So BC is the most common one. And I also see these, the LOVAS function, the LOVAS loss function here and there. And we'll see them in a few top teams as well. Then you could also have differential learning rates. So these are all different settings you can fiddle with, and that depends on the architecture, right? So I'm using a unit here. You could have different ones like unit plus plus, FPN, or different architectures. And then you decide the number of backbones, the scheduler you want to use, the metric you want to work with. So it's usually dice or IOU. Again, this is a semantic segmentation problem. And then you could also select TTA. So in this competition, as I understand, TTA was also one of the tricks. I think horizontal flip is a safe bet, so I'll just leave it at that and I can run this experiment. And for me, this is a cool way to benchmark ideas or quickly test ideas. As you can see, you get 2 minutes. In 2 minutes, you get really good feedback and you can see how your models are performing. But for today, I just wanted to use this tool to brush up what loss functions exist, what backbones are really common. Coming back to the competition, now that we know how do we work with segmentation masks, a lot of the top teams talk about 2.5D models, and I can prove that fact just by scrolling through. So let me close these tabs. But as you can see in a second, once we get there, um, that Chishen, who won this competition, says 2.5D, and a few more teams talk about 2.5D. So I assumed it's like a 2D and a 3D mix model, but that's not the case. And then, side note, for all live streams, I actually read every single discussion and understand every solution. Even though I only go through the top ones, then somewhere I discovered that it comes from this approach that Osif had shared. So shout out to Osif once more. But his approach is not combining 2D with 3D. 2.5D refers to the number of channels that go into a model. So this will tell us what's going on. But a 2.5D model has multiple slices going into it. So he says in this notebook, I'll demonstrate how to train a 2.5D images, 2.5D based model with unit from PyTorch. 2.5D images take leverage of extra depth information like our typical RGB. In this notebook, he uses three channels and two strides for 2.5D images. And then he shares some more details that are specific to this competition. But this was the kernel that got everyone started, and that's what 2.5D refers here to. So it's the fact that you're using the depth knowledge and multiple channels, and not the fact that you're combining a 2D and 3D CNN together. That's not the case. So this competition had very interesting challenges. I also wanted to give a shout out to Harshit. I think he won a solo gold in this competition. He's a 19-year-old on his way to become a Kaggle competition grandmaster. So he's really good at medical problems as well. But there were some theories and some challenges that were being discussed. So his theory, he said, was if you take all slices from vertebrae that are not fractured and run them on validation set and choose slices where the model is highly confident, then you are able to generalize. So there were all of these challenges. Heng had a discussion around 3D models and he didn't make much progress on them. There were challenges around fixing required dependencies when you were like working with inference problems or when you were trying to make an inference with the internet disabled. So you had to install some packages as well. I mention these not because to emphasize on how challenging this competition was, but because I'm using this live stream also as a proxy to help people competing in future medical competitions. So I name drop this discussion so that you can see this video probably later on and just look that discussion up if you face some errors. So I'm doing this with the intent to help people in the future working on different problems. Hopefully. There were also discussions around CVLB, and this is the one I saw first. But then I saw this one. Sorry, my throat is drying up a bit too much today. But as you can see, if there's a meme thread around CVLB, that means that there's less correlation in the competition. So that was another challenge, that it was hard to get a good CVLB correlation going. So Nishchay, I didn't recognize his profile picture. I think he changed that very recently. Okay, that's cool. But Nishchay was discussing it with Harshit, and Harshit said that he doesn't trust his CV anymore. And as you can see, there are obvious challenges around stabilizing the CVLB correlation in this competition. So apart from that, one problem, and also the hunt for 3D classification solutions, Chishan said that I, as well many others, reported that you cannot get a good score using 3D classification, whether to train directly or to train after 3D semantic segmentation as a stage 2. So by that he means many times Kaggler's come up with like these multi-stage approaches. I think Chishan had a 3-stage approach in his final solution. But you have your models working on the first stage where you take the output, and then you can use that output as a pseudo label or in some format, and then you feed that to the 3D model. So he's trying to figure that out as well, and he said this is not really intuitive. So in this competition, very few people worked or managed to make 3D models work. Salim was one of them, and he had finished fourth. But I believe there were very few people that actually landed on those solutions. So that was a bit counterintuitive, because you would imagine that that is also helpful. Apart from that, this is one baseline I also wanted to highlight. So Vladimir, who's also been sharing a lot in the current RSNA competition, shared these two base. It's one baseline but two kernels, the training and inference kernel. He had shared a EfficientNet V2 baseline where he got everyone started. Let's take a look at the leaderboard and then work our way through the solution. So that's all the context I wanted to give. But as you can see, lower is better. So looking at the leaderboard, I saw a lot of legends in the top 10. And here's Harshit with this solo gold, which is really cool to see. Ian is back. Ian also is an expert in medical images. And from what I know, he's always in the gold area for any medical competition. Chishan, of course, wins any competition. The internal joke we have at H2 is I asked him to team up with me, and he said, "Get 3 solo goals. Before that, don't talk to me." So Chishan is an absolute legend in the sense that he joins any CV competition and always ends up winning them. So far that's been true to all the competition he's been joining, at least the ones I've noticed. And I actually had this open, so this is a side note, but I just wanted to point this out. So Mobasir, who's a double GM from Bangladesh, says the following. He's referring to Chishan, but the man who knows the secret of writing simple baseline notebooks for cracking the leaderboard. Elegance at its best, and he's never seen anyone better than Chishan, who can write less complex code, very effective code, and still provide top 1% solution. So of course you'd imagine that Chishan wins the competition whenever he joins one. That is true here as well, and he did that with just 9 submissions. So that's also incredible to see. Ian did it with 8. So these are two absolute legends. Uh, I also see two more people from H2. So usually Philip teams up with Pascal and also Christoph. 3 absolute German legends, always clustered together in a team most of the times. So we'll go through their solutions and start. I'll now start going through the top solutions sequentially. One cool feature I recently discovered. So Kaggle team was telling me that they're going to add this feature soon. But this is pretty neat, and you can just go to the leaderboard after the competition has ended, and you can see all the solution links here. So if I want to read any solution, I can click on that and go to that solution. So let's start with Chishan's write up. And the reason why I pointed out that comment by Mobasir, that was because I would highly encourage everyone to check out the kernels that Chishan has shared in his write up. So he's made all of his pipeline public, all of his code and inference code as well, as I understand, public. Here it is. So I would highly encourage everyone to go through this. It's really incredible quality code. So all of these kernels, I can guarantee you, will be worth your time. But for this live stream, I'll only use the summary. He says the most important thing for this competition is to develop a reasonable pipeline followed by optimization of the model. He had designed a two-stage pipeline, and in the discussions, he clarifies. So it's a end-to-end pipeline. All of these models are trained end-to-end, but there's a two-stage pipeline to deal with this problem. And the stage one is a 3D semantic segmentation, which gives an output that goes to stage two, where the 2.5D model with the LSTM classification head gives the final outputs. So, in addition, there are two different types of classification models as well in stage two. Let's take a look at the first stage. So, the 3D semantic segmentation. He says we only have 87 samples with 3D mask, but it's sufficient to train 3D semantic models with good performance. He used 128 image size to train a ResNet 18D. So I'd shown with ResNet 34, the demo I just did, but he trained with ResNet 18 and a EfficientNet V2 small model with unit as a backbone for segmenting C1 to C7 vertebrae, 7 channel outputs. So I assume every vertebrae is output as a channel in this case. After the training was completed, the predicted 3D mass for each vertebrae, sorry, he trained these models and then in a way pseudo labeled all the examples in the training set. So I'll reiterate on this because it's worth emphasizing. There are only 87 examples with the masks. He trained a model on that with this configuration. Again, all of the code is public, so check that out for any minute details that you need. But he trained this model and then made predictions on all training examples, and then those were fed to stage two. So he gives an example of how these were worked with and how the predicted masks look like. Next, he says the next step is to prepare this data for classification. First, using the predicted 3D mask for each vertebrae, we can crop out 7 vertebrae from a single 3D image. At this moment, you have cropped, since there are 2000 examples, you crop 14,000 samples. And for each sample, there is only one single binary label. So for each sample, he then extracted 15 slices evenly by Z dimension. And for each slice, he further extracted plus minus 2 adjacent slices. This would give him 5 channels. So, example, if a 3D vertebrae has a shape like so, he extracted the following slices. And then, for example, the second one, he used the 0 to 4 slice to form a 5 channel image. This is where the 2.5D, the 5 comes from. Side note. In addition, he added the predicted mask as a 6th channel to each image as a way to exclude the effect of having multiple vertebrae in a single sample. And then there's an example with some augmentations being shown here. Now you have 14,000 3D training samples of vertebrae, and you can look at this image. So this 15 slices are then fed to a 2D CNN into a 15 by 512 hidden layer, I believe, that then goes to a LSTM head. So theoretically, this is the easiest way to deal with this. The easiest way is to like train a 3D CNN, but Shishan said that did not work. So he backed off and chose the 2.5D approach. 2.5D means that each 2D slice has information of several adjacent slices. So it's written as 2.5D. But the model is a normal 2D CNN with 5 channel inputs. And then he shares the structure of the model. You input the 15 slices, extract out features of each slice, and then follow it with an LSTM model so that the whole model can learn the features of whole vertebrae. He calls this a type 1 model. Then he also shares a type 2 model. The above one struggles with being trained for a patient as a whole, even though it can identify fractures in a single vertebrae. So that's where the second type 2 model comes in. He says the second classification is basically the same, except that it treats a patient as one sample. And this model is fed with 7 into 15 2D images at the same time. He says, however, this takes up too much GPU memory, as you would imagine, and therefore you can only use one small backbone, and that too with a batch size one. He shares some details about his final submission here. So the 3D segmentation was a 5-fold Resonate 18D, and the other one was a 5-fold Efficient V2 small on the following image sizes 128. For 2.5Ds, there were different types mixed together. One was a small Efficient V2, convex tiny. I didn't know there was a nano and a pico as well. So he wasn't kidding that you had to like really work with very small ones. But that's quite true, as you can see from here, especially for large image sizes. Um, yeah, so we learned that convex tiny can be effective. I assume the trick here is keeping the image size large. So like I'm just trying to reverse engineer his thought process. But I would imagine you could also have convex large with 128. Maybe the one smaller than that. But since he chose to keep the image size 512, I assume that's one of the secrets to um, making these submissions work or making the models work. So one thing worth pointing out, there are a lot of discussions where Chishan has answered every single question. I'll highlight only the ones I think are cool. So again, consider spending time just going through his code. It's really well written and that will answer all of your questions. But I'll summarize the key points here. Someone had asked if he had tried a transformer rather than an LSTM. He says he didn't try transformers because the sequence wasn't too long. And some details about the training time. He did use mix-up, as he says. And the fifth question was the transformation in which you do a permutation of slices. Why did he use that? And he says this was to avoid overfitting, nothing special behind it. So that's again one cool thing to remember where he did like that plus minus 2 slice selection. That was just to avoid overfitting. There are some more details about which models gave all the boosts in the score, but I'll skip that. That's all I wanted to highlight from the winning solution. So once again, this was the winning solution by Chishan. As you can see, with quite a nice, quite a really nice gap here. So this is the second place solution. And the title is segmentation plus 2.5D CNN and a GRU attention block. So we can already see similarities, and usually by the end of the live stream, a lot of the solutions start converging. So it's cool to see that eventually all the top teams somewhat converge on a 2.5D approach and a multi-stage 2.5D approach. But this is where I found that this is where Ossoff's kernel had caused the origin of all of this. So their stage one is a 2.5D CNN with a unit for segmentation, and the stage two is a CNN plus bidirectional GRU and attention for classification. Again, they used 87 studies of segmentation samples and recreated the mass labels according to the following method. They used more general 2.5D with three channels of image data, the original image and its side, so -1 +1. And they say from this complex game, they try to find the most concise and efficient solution. And it was one of the most hard drive uh, intensive competition, they say. And they wasted a lot of time loading data because there was not enough space to save the high res pseudo labeled voxel. And these are very legit challenges, if I may, because like if you look at the current G2net competition, it is quite data like storage intense as well, right? Like if you start generating examples there, it will fill up your storage drive instantly, almost instantly. This is a G2net that's going on currently. It's like I think it has a week to go. But anyways, cool to say that that problem exists almost everywhere. Soros says top solutions integrated with domain knowledge will improve results. Usually they do, and usually you see like a really large jump. In this one, I didn't see any. So like I didn't see anyone coming up with like very specific domain knowledge that gave them a boost. So it was just end-to-end models. So they share the data augmentation strategy. So they had used resizing and they had used interpolation as inter nearest, horizontal flipping, shift scale, rotate, and either grid distortion or elastic transform. If I assume everyone knows these, but if you don't, Albumentations has a really cool demo on their website where you can like see them in the browser. So that's worth checking out. For segmentation, they'd use segmentation PyTorch lib, and the backbone was B0. The decoder was unit, and they'd use a cosine annealing with a gradual warm up scheduler. They talk about how they crop the voxels. So once they had trained the segmentation model, they generalized it to all studies, and they did the same pre-processing as with the input data. After the model predicted the results, they manually looked at several images and found that the accuracy was pretty good. So then they cropped all seven cervical vertebrae separately. As you can see, this is also similar to what Chishan did, right? Each cervical vertebrae to a fracture label from the trained CSV. And again, they did some of their EDA as well that aligns in datas. They say the average of each vertebrae is about 30 slices based on this stats. So for that reason, they chose 24 slices, which will be satisfied by most vertebrae. And for cervical vertebrae with more than 24 slices, they use a simple function to get 24 slices evenly. One of the challenges for them was the dataset size. And if they saved the cropped images locally, it would exceed their capacity. So that forced them to choose the crop accordingly and corresponding slicing methodologies for stage two. After this, they talk about stage two, where they say they after this cropping that they did, the data ship is batch size 24, image size by image size, 24 channels representing the slices, and the sequence length of the GRU. The data augmentation is similar to the previous approach with just some minute changes they say. And for the model that used the CNN plus by GRU and attention, where the CNN backbone was a V2 small and resonate 50D. For some other details, they say they initialize the GRU since the original Weights in PyTorch are not very good, which means they did not use the original initialization from PyTorch. Again, it's all experimentation here, right? Like, so you have to really test out every single component when you're working with all these models. And they also added spatial dropout, which they say gives some little improvement. They did not work with YOLO, did not try Transformer, and did not buy a new hard drive. But they did open source their code, and I actually went through this. So again, it might be worth your time to go through. I can't pinpoint to what exactly was the reason between the difference, for the difference between like the top two teams. But if I was to guess, I'd say, I don't know, Chishin's end-to-end approach with like the 3D cropping and pseudo labeling, at least to me, sounds more optimized, right? Because the weights are being back propagated through the entire model, and it's I'm trying to come up with a with like put a finger on one individual thing that might have caused it, but honestly, I did not participate and I'm not on the leaderboard. So um it might be worth experimenting to like combining these approach and seeing where like if you can even improve Chishin's result. But it's cool to see that uh, Chishin's approach got him this really cool difference. And I'm still trying to figure out what might have been that single reason for that. I'll probably keep searching for that, but I don't have an answer to it. Um, Here's the third place solution by Dera, and he's also an absolute legend. His solutions are all always really cool to see. Training code, inference code, and even the video overview by himself is available. So if you'd want to check that out, the short version of it is he was hoping to get a solution which required less intense work on labeling. So this could be scaled more for the general world. He did not use the fracture bounding boxes and only used high level data from segmentation maps, which was bounding boxes of C1 to C7 by taking the outer limit of segmentation and the ratio of vertebrae volume in the slice divided by the maximum vertebrae volume. So this was really emphasized in his video as well. So I'll repeat it once again. The ratio of all the vertebrae or the volume of the vertebrae in one individual slice divided by maximum vertebrae volume in any slice. So I assume that's a form of normalization, if you may. That's what I understood from here. At least at last the models are analogous to black box. I don't think there are black box models here, Surus. So I'm not sure what you are referring to there. But you could make sense of what's going on, right? So black box is where you have like no idea what's going in, what's coming out. If we had bounding box labels instead of segmentation, these could also be used to calculate the ratios. So he says that he only used a 2.5D CNN plus 1D RNN, which was lifted from Guanshu's first place solution from the RSNA competition 2 years ago. I think I'd interviewed Guanshu about this solution, if I remember correctly. I might be wrong about that, but Guanshu is also former number one, and I think he might also climb to number one again. That's always a competition at H2O. Um, but coming back to Dara's solution, he says the bounding box pre-processing was lifted from Guanshu again, and he found it increased performance to zoom in on the vertebrae. So he used efficient V2 to predict 5 labels and the 4 corners of the bounding box and a probability if the slice has a vertebrae or not. In the downstream model, which means in the second stage models, the range of slices before C1 to C7 began in the Z axis. Also, in downstream models, the vertebrae were cropped in pre-processing. So he used the outer bounding box of all boxes in Z axis to crop the whole study in one go with a single box per study. Then this was resized back to 512 by 512, and the same augmentation was applied to the study. Then he talks about the first model, which is a slice level vertebrae labels. So he says a 2.5D CNN plus 1D RNN was used to train a model using the 87 study level segmentation. And as mentioned, the label was the ratio of vertebrae volume divided by maximum volume. This was trained on Z axis, so 32 by 3 slices per sample were aggregated to 32 2.5D images. The second position I had used 24, here we see 32. And I assume that's because he's cropping a bit more and that allows this flexibility. Actually, he's not cropping here, right? Or the cropped model is being fed here. No, I might be wrong about this because he does eventually resize. But for some reason, 32 slices were chosen. So maybe that would again constrain Dara to using smaller models compared to the previous solution, I would imagine. Okay, so there were 32 2.5D images passed through the CNN, and the RNN predicts the vertebrae ratio. RMSE was used to train these. And then there's a model 2. So the same architecture again was used to train on Z axis windows of studies with RMSE on 3 targets: slice level ratio, slice level fracture label, and maximum fracture value. And then the final model was again the same architecture, but this was used to train the full study over the final labels. And the CNN backbone was loaded from checkpoint weights of model 2, set to no gradients. And a new RNN and attention mechanism were added on top of this. He says this was the only additional difference. The only additional difference was squeezing the embedding layers in very long studies, again similar to Guanshu's approach. So he says he had used a combination of 50D and SE Resnex 50 and some more details around that. If I were to summarize this real quick, he had used a 3 model approach. And for here, the ratio calculation was one of the key factors, in the sense the volume ratio calculation in his approach seems to be like a really key detail to the solution. And this was largely, as he says, built on top of an old solution. So that also teaches us that you can always build on top of previous winners and go from there, which is why we do this live stream, and hopefully which is why all of you join this every week. Let's move on to the fourth place solution, and the title is CSN is all you need for 3D. um, Salim starts by flexing his Kaggle muscles, and he says he made the first up 10 days before deadline. So he managed to get a solo gold in 10 days. Hopefully Nishta is not watching today's live stream, otherwise I would have taunted him again. But anyways, let's read this solution. And the TLDR is it's a 2D sorry, it's a two-stage approach with a 3D segmentation plus 3D classification. So again, we saw earlier that Chishan could not work with 3D classification later on, but let's see how Salim made it work. So he says the main trick was, sorry, I'm trying to reread it again. He says after a lot of failed attempts with 3D networks for overfitting, which was the case for pure 3D convolutions, he had some options which were to inflate some 2D networks and convert them into 3D. But he says efficient nets, you could take an efficient net and start using 3Ds from second or third block. He says it works, but still tends to overfit. Or you could use a 2D with LSTM, convolutional LSTM, or transformer heads. It works. The main issue is the 3D nature is considered only at the latest stage. Or the third approach was to use networks from this particular dataset, which gave him the best result. He says even though transformers achieve higher scores on the dataset that he referred to, they don't perform well on RSNA's dataset. So for that reason, he used Action 2's implementation of a CSN model. And now he shares the detail about his pipeline. I think he has also open sourced his code. Yes, you can find his code here as well, but this gives a very concise overview of it. So he had used a unit like multi-class segmenter with the CSN architecture, CSN backbone, I would say. For the decoder, he uses standard unit decoder with upsampling, but a 2 plus 1D convolution. And he says pure 3D convolutions in decoder lead to not a number when working with FP16. For training, there was 2x subsampling. So he says just slice by 2. So just pick every alternate slice in the z axis. He also did a twice linear he twice downsampled the images and did some memory mapping to reduce overhead while reading these. So for his loss function, he had worked with the focal Jacquard optimized loss. And then some details about the augmentation, nothing worth highlighting or nothing very fancy. For classification, he had a fourfold model with global max pooling and multi-label 8 classes were used. If less than 30% vertebrae is visible, then make vertebrae's label 0 and recompute overall label. Otherwise, keep the same label. So he says he uses this trick where if the vertebrae isn't completely visible, he would recalculate the label, which kind of makes sense, right? Some more details around the training, but these are pretty straightforward, so I'll skip these. One thing worth highlighting, he had used 40 slices and 18 the original data around each vertebrae. Again, some details around the loss function and augmentation he had used. Nothing that stands out. The code is open source and so is the kernel and weight. So you can check that out if you want. But the key here was discovering that this particular data set is effective. And even though if you go look at it, transformer models were really high on the leaderboard, he figured out 3D CNNs work better with smaller data sets. So for that reason, he ended up using the 3D approach and settled on that. So this was the first one that I think had a all 3D approach, if I may. Here's another legendary team flexing their muscle. So this is the fifth place team with Kagling Dieter, old retired construction worker. If you know, you know. Philip and Pascal. They flex their muscle by saying, "Oh, we had recently ended a competition where, by the way, they won that competition. And in 11 days, they wanted to derive what they say, quote unquote, a good solution. It's quite legendary, if you may, because they finished fifth. So in 11 days, these guys finished fifth. Let's see how they did it. They also have a nice video that's linked somewhere in the comments. So you can also check that out. But let's see how they did this in 11 days. So TLDR, our solution is an ensemble of two similar approaches which follow three-stage approach. Train a 2D classifier and segmentation model for vertebrae. Use resulting model to predict vertebrae class and multiply the result with overall fracture to get 2D image level label, collect all labels per study, and train an aggregation model to predict given study labels. So here's the image overview of it. But you have this studies going through a unit backbone where you get a 3D study box as an output. Or you could also have a 3D semantic segmentation mask, which is then passed through a 2D CNN model. After grabbing all of these outputs, they pass in either the full image or this 3D study box data, based on which they crop in to a region of interest. And this is then either passed through a 2.5D CNN for the cropped region or the full image, which are then later blended and aggregated to give the final predictions. So both these logits are blended and they're sent separately aggregate they're separately aggregated to study via neural network, and even those two different neural networks, I would assume, are then ensemble together to get the final prediction. um in interest of time, I'll just leave this overview for now. But again, their code is open source as well, and you're welcome to check that out. So that was the fifth place solution. I think I'll probably end at the sixth place solution because this was also slightly different, so it's worth highlighting. Ian had finished sixth, and his overview is 3D CNN plus TD CNN. So I was trying to look up what a TD CNN is, and he does explain it here. So a TD CNN is simply a 2D CNN feature extractor with a sequence model head. And for his case, he had used a two-layer transformer. So this is the first time I see a transformer layer here. But that's what a TD-CNN refers to. The summary is he took the 3D cervical spine segmentation and then extracted individual vertebrae. The stage one models were 3D CNN and TD CNN for vertebra level classification, and then transformers for final exam classification with features extracted from stage one. For segmentation, again, if you just remember the demo I had done, you could use Unit plus plus, or DeepLab V3 plus. So he used DeepLab V3 plus encoder decoder with a 3D backbone, trained at 192 resolution. So I think Chishan had used 128. This is slightly larger than that. Models were trained on all labels, and then this was used to pseudo label the remaining data set. Pretty similar to the earlier approaches. For the stage one, once the cube is extracted for each vertebrae, he trained a X3DL to perform binary classification for each level. And he says this was straightforward to map. After the classification, features were extracted from each vertebrae. Thus, the study was represented as a 7 by 432 sequence because you have 7 vertebrae and 432 features are extracted from every one of them. So hence this dimension. Then this is fed to the what I just told TD-CNN model. He had used a 2-layer transformer for a given volume NHW. The 2D CNN extracts D-dimensional feature for each image in volume, which are then input to sequence model head. Ultimately, his model is trained end to end. He trained this model in 3 parts. First, the V2S to act as a feature extractor. And for this, he needed image level labels. He decided to pseudo label the entire data set by class activation sequence. And he says using the 3D CNN fracture classification model, he could generate a 3D activation map for each vertebrae. For that, he had to remove the pooling and classification layers and then obtain obtaining a weighted average of 3D feature maps using the layer weights. For each z axis, the max value was taken, converting the 3D feature map into 1D sequence. And then this was rescaled to 0 to 1, and then rescaled back to the original number of slices. So a single number could correspond to slices. So he took the weights, extracted the features, averaged those, normalized them to one number to represent the slices. This stepwise training occurs as follow. He trained a 2D CNN on pseudo labels, added the head, froze the feature extractor, and then fine-tuned the entire model end to end. For stage 2, he says now that we have essentially converted each study into a sequence, we can use transformers to model the final output. He says he used a 3-layer transformer on 3 separate inputs. The first one was 7 by 432. The second one was 7 by 256, which came from TDCNN. And then 7 by 688, where he fused the above two. So I think if you add these, you get this number. So he had used these inputs separately and then also combined them together. The final submission was an ensemble with the following weights. Adding mask as a separate channel did not help. I don't think other teams had used this either. So other teams had added like the vertebrae info as we just saw as a separate channel, but not the mask, right? And then masking out non-segmented parts did not help, or extracting slice-wise features and training models also did not work for him. So his secret was TD-CNNs and then averaging and combining the feature extractor for all of these. In interest of time, I'll probably wrap up here. So we also have some more solutions left, but I think this is a good point to end this. We still learned a few tricks, hopefully together. I'll probably live stream recently ended solutions after this, but I'll come back to the medical ones since the RSNA competition is still going on. We'll meet again, I think, on the Sunday after this because the upcoming one is New Year's and I usually make a video on New Year's. So I'm not sure if I'll put out 2 videos then. But you can keep an eye out on my Twitter. I'll probably announce if I'm doing a live stream then. Regardless, I'll keep these going every Sunday in the new year. So thanks for joining. This will be the last Kaggle Top Solution live stream for this year. Consider subscribing to be notified of the future ones, and I'll see you all in the next year. And Merry Christmas to you all again.